Good afternoon, everyone. I want to welcome you to my lecture today. Of course, I observed on Monday, majority were not around because of I was told maybe a job fair was actually going on. So I think I'm going to repeat what we did on Monday because what we did on Monday is very, very crucial. And because of that, and you need the knowledge, in your research or the Adams work. And that is why I want to repeat that. So I need you to pay 100% attention. In case you don't understand, please ask me question. Now, this is the problem. We are consulted. It's actually going to be on bus study. Okay, we are consulted by a client that really want to know if there's a significant difference between uh, the arrival of a bus, like I mean, we're talking about times in low income neighborhood and high income neighborhood. So you really want to know whether bus arrive later, okay, in low income neighborhood compared to higher income neighborhood. And of course, in United States, they operate a busing system where children, school children actually enjoying ride, to school, and they also enjoying ride back home. Now, the question now is, we are trying to see if, uh, you know, bus arrive later, okay, later in low income, okay, neighborhood, okay, if bus arrive later in low income neighborhood, compare to higher income, okay, uh, neighborhood. Now, when you take a look at this question, if I really want to figure this out, this is synonymous, you know, testing effects of neighborhood income on late times. Okay. But this is what happened in the sampling use. Okay. Uh, they collected eight stops, eight stop each. Okay. Eight stops were randomly choosing from both neighborhood. Okay, so which means for low income and high income, okay, we got 1, 2, 3, 4, up to 8 for both of them. Okay, we're talking about stops, numbers of stops. Okay, 8 in the low income and 8 in the high income, and the 8 the 8 in low income and 8 in high income were selected randomly. Okay, and on each stop, they consider 5 arrivals, 5 bus arrival time on each. Okay, if you take a look at the stop now, okay, we have 5 arrivals that they consider, like 5 buses arrive. But you know what? The response, we got a response variable where we're actually going to have what I call a schedule time. Okay, so schedule, or let me just say arrival minus schedule. Okay, the arrival time minus schedule time. Even though in reality, even though what we actually have in mind is that, oh, bus should arrive on time. Okay, which is, if bus arrive on time, if the schedule time the same as arrival time, we expect our y to be equal to 0. If y has been 0, if the difference has been 0, there's nothing to worry about. But we notice the difference has not been 0, and that is the reason why we really want to figure out whether we used to observe late arrival time more in the low income neighborhood compared to higher income neighborhood. Now, I'm going to tell you the naive method that some researcher will use, and the naive method is not appropriate. Okay, so the naive method they're going to use is to fit a simple linear regression where I'm actually going to have late time. They will be regressing that, regressing that on intercept and neighborhood. The neighborhood here is a categorical predictor. The neighborhood can be low or high. We're talking about income, okay? Low income, okay? High income, okay? Now, the intercept here, of course, is actually talking about the baseline for the late times, okay, without putting into consideration the effects of neighborhood. Now, why is it that this approach is not going to be okay? This approach is not, because if I want to use this approach now, you know what I'm going to do? I can actually say, okay, let me find the average of late time here. Okay, I'm going to have one data value. Don't forget, on each stop, we observe 555, right? You find the average. How many data points are you going to have at the end of the day? For low income, it's going to be 8. For high income, it's also going to be 8. Okay, that is too small in terms of sample size. Okay, you are using an aggregate data. Using an aggregate data, you've already nullified the effects or potential effect of what stop can, of stop, because stop here, okay, is the observation is being repeated, like having 5 arrivals in a particular stop. That's a repeated measure. We expect a correlation to exist within a particular stop. Okay, so this approach is not going to work, okay, for this, because being a repeated measure. Now, what are we going to consider? Well, what do we need to do? So what we actually need to do is to use a mixed effect model. We're actually going to use a mixed effect model. In a mixed effect, like here, this is just entirely fixed. This is fixed. Okay. Now, I'm actually going to I'm going to consider one in the mixed effect model. Our four of us consider a situation where we make intercept to be random. Okay. And I'm actually going to have late times 1 plus neighborhood plus 1 nested in stop. Now I'm going to explain this to you right now. This is late times, okay, which is more or less like we're talking about delay, the difference between the arrival and the schedule time. This guy one here is trying to is the delay, the baseline value of late time. The baseline value of late time. This guy here is the predictor. It's a categorical predictor, and this is fixed. Okay, this is fixed right here. Okay, the coefficients here, which is what we call the beta. Like for instance, you know, when you test for the effect of this, the coefficient either here or here. Okay, you know, there's something that you do. Beta equal to 0. Alternative, beta greater than 0. Okay, when the coefficient associated with the neighborhood is positive. You know what I mean? If it is positive, okay, it means boss arrive later in a low income neighborhood compared to high income. Before I move into this, let me also tell you this. This simple linear regression here is the same thing as a two sample t-test. You know, in the two sample t-test, you're testing that, let's say, low income minus higher income equal to 0 in the alternative, then this minus this greater than 0. Now, this is the average late time in the low income neighborhood, the average late time in the higher income. So if the difference is greater than 0, then it is more. The late time is more here. So when this is greater than 0, it is the same thing as testing beta greater than 0 when you test for the significance of slope in regression. So if this is true, this guy is also true. So simple linear regression with categorical predictor is the same thing as you just categorical predictor provided, you know, I got 2 levels for the categorical predictor. It's synonymous with 2 sample t-tests. So 2 sample t-tests cannot be used. Simple linear regression cannot be used. But coming into here now, okay, what have I done? I incorporated this. What is the meaning of this? I'm going to tell you now. I'm trying to say, I'm having a random intercept. Whatever you see here, okay, you know, 1 is an intercept, right? It is what I'm actually, I want to account for the variation in that. So I'm trying to say, you know, the late times, it differs, okay? The late time differs across stops, irrespective of whether they are from low income neighborhood or high income neighborhood. There's a variation in stops. That is what this guy is talking about. Variation is. This is like trying to tell you the baseline for late time is not the same across stops. Does that make sense? And that is why we are accounting for that variation. Random effect indicates something varies. Okay, that is what this guy is actually talking about. So this is fixed, but this is random. And the random here is random intercept. So if the neighborhood is fixed, what are we trying to talk about? We are still saying that we're still saying here that effect of neighborhood on late time is the same across stops. That is the meaning of the fix. I'm going to say that again. Effect of neighborhood income on late time is the same across stops. That is what we mean here. But here, the baseline time, the baseline value of the delay or of the late time differs across stops. That is what this guy means. Now, if I call this guy model 1, and I want to have, there's another possibility that I can also consider where I got late times, okay, on 1, plus neighborhood plus neighborhood plus 1 plus neighborhood nested in stop. Please, I need you to pay attention. Okay, here, I want to have random intercept and random slope. Okay, this is random intercept, then random slope. Now, what am I trying to say here? In addition to accounting for variation in stops, okay, accounting for variation in stops, putting into consideration the late time, we are also saying effect of neighborhood income on late time differs across stop. You can see there's a different, I'm actually going to call this one model 2, and I'm going to call this guy model 1. When you have a repeated measure, you need to first start your approach, okay, where you're actually going to incorporate a random effect on the intercept. Then you also incorporate a random effect on the slope. So this is having, two of them having, random effect for intercept, random effect for slope. So what I have here is a random effect structure of the model. This is still fixed. Okay. Now, when you take a look at these very two now, okay, the two of them they are competing. For instance, how am I going to know which one is better out of the two? Then I can conduct a likelihood ratio test, or using nested ANOVA. I'm actually going to test under the null hypothesis. It's going to tell me random intercept is fantastic. Alternative, random effect for both. Okay. Now I'm actually going to have ANOVA into the simple model. The simpler model is a random intercept only. Simple. I'm going to start with model 1 now. The one with the random intercept only. Model 2, the complicated. This is nested ANOVA test. Is going to return a p-value. When p-value is less than a reasonable level of significance, maybe 0.05, you're actually going to reject this and go with this. Otherwise, you're going to stay with the random intercept. But let me also say this. Let's say, for instance, the p-value is less than 0.05, and we're here. If that suggests that the two, model with random intercept and random slope is going to do a great job, then there is something more you need to do. You need to consider, because if you have two effects in a model that are random, they could be correlating, they may not correlate. So we need to be able to test correlation effects. Okay, so this is test of correlation effect. Why am I testing correlation effects? Maybe my model suggests a random intercept and random slope, because the two are random. There's possibility they could be correlating. Okay, so or not. The null hypothesis is actually going to say they are uncorrelated. Alternative is going to say they are correlated. They are correlated. Alternative is going to say they are correlated. Okay. Now, what is the model? This guy here is a model for correlated. Correlated. If I want to write model for uncorrelated, Now, I need you to take a look at module 3. Uncorrelated, we have is 0 plus neighborhood. Here you can see random intercept, but in the random slope, you're going to put 0 plus that. So module 3 here, okay, this module 3 is uncorrelated. Uncorrelated. Module 2 is correlated. So if I want to know which one is going to work great between situation where the two effects are correlated and the two effects are uncorrelated, I'm still going to use ANOVA. But if I want to use the nested ANOVA, the very first module I'm going to write is going to be the one for uncorrelated. Uncorrelated is in the non-hypothesis. Okay, so uncorrelated module 3, comma, module 2. Go ahead. Oh, okay. How you do that? Yeah. Now we we have a way to indicate this now. So what we actually I think I'm gonna attach a material today on how I think that's a very good question. Okay, I want to run my data in now. How am I going to know that I want to use a random intercept module, or I want to use both random intercept and random slope? I will attach a material today in R that will help you out. You're welcome. But let me tell you this. When you go for this one, the result is going to come in two forms. Fixed effect regret one, that you already know about. And there will be variance component. In the variance component, you're going to have a variance for intercept and the variance for slope. Okay? So, is there any other question on this? Go ahead. That's a very good question. A very, very good to the core. What happened is your question is if the number of independent variable is more than one, do we have a random intercept for them, or do we do interaction? Let me tell you, in repeated measure, we do interaction, we do random effects for both. There was one example I gave the other time, and I will use that here. That's a very good question. Oh, okay. Let's think of other effects that could make, even within this, which other effects that could affect late time, as in apart from the neighborhood income. Can we think of something? Eh? Oh, weather. Okay, thank you so much. Now, which we're going to like, or should we call that season? Season in the year, whether it's summer, winter, which is going to be categorical, right? Okay. Now, what we can do is, if I have this guy and this guy, we can, four of us, before we go into repeated measure approach using random interval or random slope, we can, four of us, look at is interaction going to be beneficial? First, we settle for that one. Let's say, for instance, neighborhood and weather interact. Of course, we know how to test that, when it is significant, right? Which means we need it. Now, if it is significant, we need it, okay? So which means in a repeated measure model, I can, if I have late time, okay, 1 plus neighborhood, I'm taking n because of my time, n, and weather, w, okay, then plus, okay, here, fixed. This fixed. I'm assuming that we all know if we've considered all the weather, then it's no longer a random variable. Fixed. Then right here, we can actually consider one random intercept for intercept. We can also consider that this. We can also talk about this. Okay, in stop. Look at that. We can actually nested so many factors. But how do I know whether what I've done is going to be appropriate? We have a way to test, like that was what I used ANOVA, nested ANOVA. Now, you know what I'm trying to study word here? Oh, the baseline late time differs across stops. Okay. Now, the effects of neighborhood, okay, on effect of neighborhood income on late time also differs across stops. Then here, I'm also saying effect of weather. Now, effect of weather on late time also differs across stops. That's what I mean. So to answer your question, yes, if it has as many as possible variable, if we have a doubt, we can assume it to be random. So when I assume it to be, let's say for instance, do you know that here another module here is look at that. If you compare these two models, this is complicated. This will be in the non-hypothesis. What am I? I'm only considering random effect for intercept, and that effect. We could have situation where one effect, okay, like effect of neighborhood here, okay, on the late time differs across stop, but I'm trying to say effect of weather does not differ across stop. That is why it is fixed here. So if you compare this and this is complicated to this. In the non, if I call this one, let's say this guy module 1, and I call this one module 2. If I want to see which one is better, it's going to be ANOVA. Then the simpler module first. The simpler module is going to be this one. The simpler one is the one that have, you have a fewer numbers of effect that have that is randomized. Okay, so I'm going to mode 1, comma mode 2, and in my non-hypothesis will favor this. Alternative is going to favor this. So what I'm going to advise that you should do, consider possibility. In statistics, we exploit. In research, we exploit. Which one? I don't know the one that is good until I've explored all my models. So to your question, of course. And do you know that another complicated model here, if I want to make this one, if I want to produce another version of this, I can also write what have I done? I've introduced interaction between this and this, but this interaction here is fixed. If I want to make it more complicated, I can also put interaction to be nested. But it's good. Don't forget, the stop here is what you collect observation on. In Adam's work, I know you're going to have ID, right? And a lot of observation in a particular ID. That is acting like a stop here. That is what makes it a repeated measure. Does that make sense? So this is it. Any other question? Go ahead. You have to do what? Yeah, you can. It doesn't. Let me tell you something. Just like what I used to say, it doesn't take anything from us exploring. You can also consider interaction. But what is going to tell you at the end of the day, interaction may not work. If it is not significant, then I'm not going to use it. If it is significant, then it should be in the, because let me tell you this, even if you introduce a random effect on a particular variable, but if if the effect of neighborhood income on late time is not consistent. What do I mean by not consistent? Effect of neighborhood changes due to weather, then this and this they are interacting. If I ignore that in my model, that will be model misspecification. If a particular effect is very, very important and is missing in a model, where does it go to? Can somebody tell me where does it go to? Where does it go to when it is missing? Where does it go to? It go to somewhere. Where? Can somebody tell me? It goes to the error. When it goes to the error, what will happen to your error? If that effect is significant, your error will not behave well. We normally want one situation where error behaves well, which means assumptions that you test on the errors, there's going to be issue with that. So, because this is your assumption on the error. You know the meaning of this guy? You are trying to say some other variables that your model did not capture. What are you trying to say? On average, their effect is more or less zero. What if their effect is not zero? Then there's going to be an issue. Everything is going to, is actually going to go back to the error. What are we trying to do? We're trying to consider if you take a look at this, when we consider this, if we did not consider this and we only consider just this, and this guy here is significant, then it will affect the error, because our effort is to minimize the error. And we have to think round the box to see what effect do we actually need to bring in that may potentially influence the response. Does that make sense? And that is exactly what we're trying to do. So, I told you the other time, when you use a naive method, you will get a result. But it is not all result that makes sense. In fact, I laugh when I see some people, they get significant results, right? Significant result because the p-value is less than alpha. They're going to be celebrating. Okay, what if they are using the wrong approach? It's more or less the same as somebody who commit offense in the state of Minnesota, ran to California, and the court in California, the cop, they arrested him and they try the person, and they're able to establish the fact that he committed the offense. But let me tell you this, even though they have done the right thing, but they don't have a territorial jurisdiction. Did the person break the California law? No. The person broke Minnesota law. So the same thing is when you use a naive method and you get a significant result and people are celebrating. No. So the significant result that you get is not just using a model, but am I using appropriate model? Is there any other question? Go ahead. Okay, that's a very good question. Actually, what took us to miseffect model was because, there are so many reasons that could take one to miseffect model. Let me first tell you number one reason why we could go to miseffect model. If I'm looking at the effect of neighborhood on late times, neighborhood income on late times, and maybe I have 4 categories of neighborhood income, but I only use just 2 of them. That make that effect to be random because I choose only 2 out of the existing classes. Do you understand now? That is one of the reason why in our model, one of the independent variables should be random. But what if in a situation whereby the observation, here we're using stop, and stop, we observe 5 things because the 5 buses arrive daily in every stop, whether in low income neighborhood or in higher income neighborhood. Now, because I have 5 stops, I'm sorry, because I have 5 observations within one particular stop, then that has created an avenue for repeated measure. And the moment you have repeated measure, of course, automatically the statistical technique for repeated measure is mixed effect model. So which means we're now going to say, okay, the intercept, this guy, okay, put it, without even considering the neighborhood income, stop itself as a variations. That is what we mean initially here when we nested intercept in stop. Okay, so we are trying to tell the world, because in the conventional, what this one is trying to say, it's the same, they have the same baseline. That is what this guy is trying to say. But even though we incorporated the fixed effect here, we also incorporated the random effect for it. That there could be a possibility. We can't say for now until what come out from the statistical test. And that is the reason why it's always easy to let's consider possibility and see what the test. Most of the time, or let me just say sometimes, some researchers normally decide and say, okay, what to test. I don't belong to that kind of research. I explore. It doesn't take anything away from me. If somebody is going to tell me, why is it that you didn't consider a particular effect? I say, I didn't consider it because it's not significant. And this is the result. But I'm not going to say because I felt that it's not going to be significant. You understand what I mean now? So stop. So if I now nested neighborhood in stop, I'm now trying to say effect, because the neighborhood here that is fixed is trying to say effect of neighborhood on late time is the same across stops. But this guy here is saying, no, I'm actually going to have, when I put into consideration stop, I will have so many different lines. So the effect of neighborhood on the late time is not the same across stops. And this guy, effect of weather, not also the same across stop. Effect of weather on what? Effect of weather on the late time. We always go to, so there's possibility that, this is good. But how am I going to know? What I'm going to know is I'm going to write possible models. Then I will start comparing. But if I want to start, I will first start with the random intercept. If the random intercept is okay, I don't need to go to any other. And how am I going to know? If I test random intercept against maybe random intercept and random slope, and that tell me a random intercept is okay, then if I incorporate random slope, even though I'm going to have an effect for it, but it doesn't really explain significantly variation in the response, why am I wasting my time? I actually love statistics because there's nothing like authoritarianism. Like, what I mean by authoritarian, you can't be an authoritarian in statistics. If you get anything, they're going to say, okay, how? Then, this is how I got it. Have I answered your question? So stops here remains the observation. I mean, maybe I'm going to call it like an experimental unit that was observed more than one time, because 5 buses came into one stop, and there's going to be correlation even within stop. You understand what I mean? And that is the reason why At the end of the day, we need intra-class correlation. The intra-class correlation is just going to be, okay, the variance of a particular effect I'm interested in divided by the total variance. And don't forget, those ones that are fixed, their variance is 0. It is only those that are random that, we're actually interested in their variances. Is there any question? I think by now you should but you know what I'm going to do, the how to do that in R. It's not going to be a serious code. I can assure when you see what I'm going to share that with you today. Okay, try possibility, and at the end of the day, and see, you're going to see the one, but start with a random intersect force. Any other question? I think I'm going to stop here today. So make sure you all stay safe and have a lovely day.